So in this video, we're going to discuss the first of our carbonyl compounds, carboxylic acids and their derivatives. I'm choosing to do carboxylic acids first because the nomenclature that we're going to use for aldehydes and ketones, common nomenclature anyways, for small aldehydes and ketones, comes from the nomenclature in the common system for carboxylic acids. So I just feel like it's probably better to do these first. And so it might look like it's going a little bit out of order with the textbook, but it's just a little easier for teaching and learning purposes. So basically the carbonyl group, and I'll just draw out generically what I'm talking about here. So R for rest of molecule. We have a carbon that is bonded to an oxygen with a double bond there, single bond to R, whatever that may be, the rest of the molecule. And I'm just going to write like a Z here. So this right here is going to be important to us in a sense that in this particular chapter, we're going to be dealing with groups. Z, right, is a group that can be replaced potentially by an incoming nucleophile. When we do aldehydes and ketones, Z will be a group that cannot be replaced by a nucleophile. So let me just draw that out. We either have, in other words, an atom that is essentially more electronegative than carbon, or we have an R group, like another R group, or a hydrogen. So in the case of an aldehyde, we'd have a hydrogen there. In the case of a ketone, it would be just another R group, or, you know, it could be a group that's different from the other R. It doesn't have to be a symmetrical ketone, but essentially we're dealing with a molecule where either that atom is going to be like a nitrogen or an oxygen, right, or a sulfur or something. Well, we'll stick to nitrogen and oxygen, or it's going to be R or a hydrogen. So that will be where we're headed. And this group right here, this C double bond O, this is what we call a carbonyl. So that is a carbonyl group. The carbonyl group is one of the most important functional groups in organic chemistry. There are millions of compounds that contain them. They're abundantly ubiquitous in nature, and they play many, many important roles biologically. Those two groups, again, for Z, either an atom that's more electronegative than carbon, and in that case, this group can be replaced potentially by a nucleophile. In the case of aldehydes and ketones, we'll be dealing with the other group of carbonyl compounds where this cannot be replaced by an incoming nucleophile. All you have to do is imagine or look up the pKa of the conjugate acid of the leaving group to decide if it's going to be a good leaving group or not. Right? So in other words, if I'm dealing with an R group, that's R minus would be leaving, right? So if I put a hydrogen on R minus, I essentially get either an alkane or an alkene or whatever, right? So I'd end up with some kind of hydrocarbon. pKa of that is like, 40 or 50 or something. So there's no, that's not leaving, right? R minus is a really, really strong base, not going to leave. So when we're talking about an atom that is more electronegative than carbon, in this chapter, we're going to be focused on oxygen or nitrogen containing compounds. So carboxylic acids and their derivatives will be like esters, amides, acyl, chlorides, that kind of stuff. So the first thing we're going to do is deal with the carbonyl compounds. With a group, say Z, that can be substituted for a nucleophile. So in other words, we could have a carboxylic acid, so R, and then the carbonyl, and then OH, right? So hydroxide is a strong base, but if somehow along the way that OH gets protonated, water can leave, right? So carboxylic acid would have a leaving group, would be equal to hydroxide, and its conjugate acid would have a pKa of 15.7. So that makes water a weak base. It's a weak acid. H2O is also a weak base, right? We also have the ester functionality. So instead of OH, we would have OR, and it doesn't have to be the same R's on the other side. We can put a little prime there to say it doesn't necessarily have to be symmetrical, but the leaving group essentially would be an alkoxide anion, right? And the alcohol would be its conjugate acid. pKa of an alcohol, depending on the alcohol, is around 15 or 16. So water or an alcohol are pretty equal in their ability to take off. Another derivative of a carboxylic acid would be an acyl chloride. So remember the acyl group is this R, C double bond O. There's your acyl group right there. And we'll put a chloride on there. So this is some people call them acid chlorides, right? They're derivatives of carboxylic acids. Essentially, what does that even mean? A derivative of a carboxylic acid. It's not just that they look like them, right? Because aldehydes and ketones also have a carbonyl. You're essentially saying, can I make a carboxylic acid out of this group, right? Or could I take a carboxylic acid and turn it into one of these other groups? That's a derivative of a carboxylic acid. So an acyl chloride or acid chloride, whatever you want to call it, the leaving group is chloride, right? It's the halide ion, so Cl minus. HCl would be its conjugate acid. Remember, the stronger the acid, the weaker the conjugate base, or in other words, the weaker the conjugate base, the stronger the acid. HCl has a pKa of about -6. Remember, the smaller the pKa, the stronger the acid. So chloride is like, the pKb is like, 1 times 10 to the -20th or something like that. So not exactly even basic. It's pretty neutral, right? So really weak, which means that an acyl chloride is going to be pretty reactive because chloride is the leaving group and it's pretty awesome at leaving. Then we have these other things. It doesn't have to be oxygen. It doesn't have to be a chloride. It could be a nitrogen. And we have options here. So we've got the nitrogen could have 2 hydrogens bonded to it. It could have 1 hydrogen. We usually stick it above or below when we're going to write an R group. And I could just make this like a different R group. It could be the same. It could be different. But essentially, we could have these options where all three of these are amides, right? So we have the carbonyl, then we have a nitrogen, and it's either got like two hydrogens, one hydrogen and an R group, or we could have like two R groups. And the R groups don't even have to be the same, right? So all of those are going to be amides. I'll just lump these all together and just say that essentially the leaving group is some derivative of ammonia. We'll put approximately, and we'll just stick to the first one there and just imagine that that's leaving, right? That's a really strong base. Ammonia would be the conjugate acid, but that's a weak base. If we protonate that, we have the ammonium ion. So if you want to talk pKa values, the ammonium ion has a pKa of 9.4. So I should write down here, this will be special for us. These are fairly unreactive. And amides only will undergo substitution reactions when the amide ion is converted to ammonia. And we just saw its conjugate acid is the ammonium ion. So that's worth noting. Those are going to be fairly unreactive compounds. When we get into reactivity, structure and reactivity instead of just structure and nomenclature, we'll come back to talk about the amides. They're probably one of our least reactive carboxylic acid derivatives. You'll find also when we get into reactions that we introduce a few new functional groups. So I would like to also mention anhydrides, and I would also like to bring in nitriles. So just so that we can have a few more reactions to run through. In terms of nomenclature, so this is just going to be carboxylic acids and their derivatives, and we're going to save aldehydes and ketones for a separate section. Nomenclature for these. And I'm going to start with carboxylic acids because we have a common naming system for any carboxylic acid with 6 carbons or less. Those acids were found in various compounds hundreds of years ago, and scientists gave them common names based on those products they were found in, right? So we'll talk about those 6 and then also their IUPAC nomenclature. I'm going to start with carboxylic acids because naming carboxylic acids will be the basis for naming any other carbonyl compound. So this is how we usually abbreviate a carboxylic acid if you don't feel like writing out the whole word. Again, we have an sp2 hybridized carbon. So in other words, the electron geometry about here is 120 degrees, right? This thing is flat. In other words, it's planar. This right here is the carboxyl group. So that other thing, that C double bond O, is a carbonyl. This is a carboxyl group. IUPAC nomenclature, pretty straightforward. We're going to replace the E of the alkane with oic acid. So you name the parent hydrocarbon And you're going to replace the E of the alkane name with oic acid. Like if you had ethane, you would, if it was a carboxylic acid, you would have ethanoic acid. You're going to number any substituents. You're going to use numbers. For any substituents. And you should know that carbon number 1 is always the carbonyl carbon. So you start counting from there. Common nomenclature. These carboxylic acids, if they have less than or equal to 6 carbons, they are going to be named after compounds that contain them. Usually having either Latin or Greek etymology. Instead of numbers, so you can have substituents on a carboxylic acid in common nomenclature. And so rather than using numbers, we use Greek letters to indicate position of the substituent. So alpha would be the first carbon after the carbonyl carbon. So carbonyl carbon is always number 1. Carbon number 2, using common nomenclature, would be alpha. So that's going to be carbon number 2. Beta would be the third carbon. Gamma is 4. Delta is 5. And epsilon is 6. So if you're dealing with a carboxylic acid with less than or equal to 6 carbons, and you have a substituent on one of those carbons, you're going to use a little Greek letter to denote its position instead of a number. So let me give you some examples. We could have our smallest carboxylic acid, which only has 1 carbon. IUPAC, so let's do it this way. I'll put a little I for IUPAC, or systematic nomenclature, and I'll put a little C for common. So if we had an alkane with just 1 carbon, we'd have methane. So we're going to drop the E and add oic acid. So this will be methanoic acid. The common name for methanoic acid, it's named after little fire ants. Methanoic acid is the compound that the fire ants will inject into you when they bite you. It burns, right? So it's named after the Latin word for ant, which is formica. So we call this formic acid. The next one is probably familiar to you. 2 carbons. This is ethanoic acid, right? Because it would have been ethane. This is actually named after the Latin word for vinegar, which is acetum. So we call this acetic acid. If we have 3, a total of 3, right, carbons. Remember also that, I'm just going to save space and not draw the geometry in here. Remember that always your carbonyl carbon is number 1 in terms of its position. So if you have substituents, that's number 1, and the next one over is number 2. Or if you're using common nomenclature, that would be the alpha position, right? So this would be propane if it was an alkane. So this is propanoic acid. And the common name is not too far off. 3 carbons, let me move this over so it looks like it goes with that, is actually propionic acid. And this one wasn't actually named after a specific compound. It was named essentially because it's the smallest carboxylic acid that actually shows characteristics of a fatty acid. A fatty acid is a carboxylic acid with just a big long hydrocarbon tail. That's all. So it's got that carboxyl group on the end, but it's usually like, like oleic acid is like 16, to 18 carbons long. The fatty acids found in coconut oil, when we call them medium chain carboxylic acids, those are like 18 to 20 or something like that, somewhere in that ballpark. So we're talking long, right, chains. And they're fatty, they're relatively nonpolar because the only point of polarity would be the carboxyl group. And then you get this big long hydrocarbon tail. Well, propionic acid or propanoic acid is the smallest one that actually starts to display characteristics of a fatty acid. And a propion actually means first fat. So that's the lamest of all the common names, in my opinion. It doesn't actually come from like any specific plant or like, compound or whatever. The next one, and I'm going to try to save a little bit of space here, is 4 carbons. So I'm going to put these little methylenes in parentheses so that we can consolidate. So essentially you're counting 4 carbons, and that would have been butane. So this is butanoic acid. The common nomenclature for this, it's actually named after the Latin word for butter, which is butyrum. Oops, I'm writing butyrum. It's butyric acid. So butyrum is the Latin word for butter. Butyric acid or butanoic acid is actually the carboxylic acid that you find in butter when it goes rancid. And when I tell you that this stuff smells bad, like words cannot express how horrible this particular molecule smells. When we get into reactions of carboxylic acid derivatives, esters, to make an ester from that, we can actually make imitation pineapple flavoring, which smells nothing like butyric acid, but you start with it. And it's kind of one of the most impressive reactions just because of the transformation, aromatically anyways. No pun intended, because it's not an aromatic compound. This next one has 5 carbons, right? So we've got pentane derivative there, so it's pentanoic acid. This one's kind of cool. So this one is named after valerian root because pentanoic acid is found in valerian root. It's used for people if they have trouble sleeping. It's one of those natural remedies, right? So we call this valeric acid. And then the next one, or the last one, I should say, that we will give a common name to, because remember it's less than or equal to 6 carbons. So if we have 6, this would have been hexane, so this is hexanoic acid. This one is actually named after a goat. So the word for goat is caper. So we call this caproic acid. Hexanoic acid smells a little bit like a goat. If you've ever worked on a goat farm or been around a male goat, they have this sort of like, I don't know, I guess they assume it's a cologne, but to us it's this musky, disgusting smell that they think they're just going to use to, like, attract a mate. That's caproic acid. So we name that after a goat. If you have a substituent hanging out, let's do an example where we've got a substituent hanging out somewhere. Let's do, say, we'll put an OH here as a substituent. So if you want to use IUPAC nomenclature for this, the carbonyl is going to be carbon number 1. So I'll put a little 1 down here. The second carbon over will be carbon number 2. So I'll number them up here, 3 and 4. So this is some form of butane, right? But we're going to drop the E from the alkane and add oic acid. So for IUPAC nomenclature, we have to tell somebody that we have a hydroxyl group. That's our substituent. So the star of the show for this is the carboxylic acid, right? If you want to look at, I'll share, I have a little chart. Actually, I think it's in the notes, the lecture notes, for priority for naming. One sort of general rule that we typically follow is how oxidized the compound is. The higher the oxidation state, or how oxidizable it is, takes priority. So instead of naming this after an alcohol, we're going to name it after the carboxylic acid. So that means that the OH group is not a functional group. I mean, it's a functional group in a sense that you could use it functionally, but in terms of nomenclature, this thing will be named after the carboxylic acid. And that means the hydroxyl group is a substituent, and it's hanging out on carbon number 3. So 3, when a hydroxyl group is a substituent, we call it a hydroxy group. And then it would be butanoic acid. Acid is a separate word. Common nomenclature, and I'll use a different color here. This is always going to be carbon number 1. So that's just where you start from, right? It doesn't have a little Greek letter because we're not using any number to indicate that you're hanging out on the carbonyl carbon, right? Because we're naming this thing after the carboxylic acid, so it's implied. But what that means is that this carbon over here is our alpha carbon. Let me get rid of these. People are usually pretty okay with the numbers. It's these little Greek symbols that they have a hard time with. So we have the alpha carbon is right next to the carbonyl carbon. We have the beta carbon, which is the next one down, right? And then gamma. So we have beta hydroxy butyric acid. So we do not have beta hydroxybutanoic acid, and we do not have 3-hydroxybutyric acid. So don't mix those up, okay? Let's see what else. Let's do one more. We'll do a line bond structure just to get used to dealing with those. And I guess on this carbon, we could have, I'm not doing stereochemistry because we don't have to worry about that. When we're just learning how to name these. So a UPAC nomenclature would tell us that that group, that substituent, is a methoxy group, and it's hanging out on carbon number 2. Remember, the carbonyl carbon is always carbon number 1. So we have 2-methoxy. And how many carbons do we have anyway? So we've got 1, 2, 3, 4, 5. So that is a pentanoic acid. Common nomenclature. So we'll get rid of these numbers now that we know how many we have. And we'll say that this is our alpha carbon, beta. You don't have to do all of these. Obviously, your substituent's on the alpha carbon, but I just wanted to show you as a reminder what they're called. So we have an alpha, a beta, a gamma, and a delta carbon, and our methoxy group is on the alpha carbon. We will use the word alpha carbon, or we'll talk about the acidity, actually, of the hydrogen that hangs out on the alpha carbon. When we get into aldehydes and ketones, we can do some pretty cool chemistry at the alpha carbon. It's pretty special. So what we have here for a common name would be alpha, methoxy, and there's 5 carbons, so that is a valeric acid. Cool. Let's move on to our next group. We could do acyl chlorides. Once you get the carboxylic acids down, and usually it's the common nomenclature that people end up having to memorize. Some of these names I'm sure you've heard of before: acetic acid, formic acid, right? Valeric acid, maybe. But once we get the carboxylic acid nomenclature down, anything else that we're going to name for the rest of this class is going to be easy. So essentially our acyl chlorides or acid chlorides, we're going to replace the ic acid with eel chloride. So replace. Now it could be for my UPAC or common nomenclature, but we're taking the ic acid part away. And we're going to replace it with eel chloride. So YL. Always sounds weird to hear the rules without seeing an example. So let's just put out a couple of examples. I have a derivative here of benzoic acid. And instead of benzoic acid, we're going to drop the ic acid and we're going to put eel chloride. We call this benzoyl chloride. You have probably heard it, some of you maybe, as benzoyl chloride. If you've ever used one of those like to clean your face or whatever, and it's got like acne medicine in it or something, they call it benzoyl chloride. There's the molecule. So, but we call it's benzoyl is the pronunciation. So that's benzoyl chloride. It is a lot more reactive than benzoic acid, as we'll find out. Chloride is a far better leaving group than hydroxide, right? So you're getting kind of the idea. There's a lot of common stuff that happens in organic chemistry. The awesomeness of the leaving group, so the weaker the base, that's like something you can count on, right? And if you don't have an awesome leaving group, what do? Well, we've been noticing there are ways to convert it into an awesome leaving group. In this class, we've been just focusing on turning it into a weaker base. There are other things that you can do to encourage a group to take off. Can turn them, turn it into like nitrogen gas is the best leaving group. But for Chem 42, 44, we're sticking to, hey, just protonate it if you're having trouble. So let's do one more real quick. One with a substituent maybe. So let's stick something, I guess, here. So a UPAC nomenclature. Follow our little theme here. On carbon number 2, right, we have a methyl group. And so we have 2 methyl, and then we have 1, 2, 3, 4 total carbons. That would have been a butanoic acid, but instead we're going to drop the ic acid part. And we'll end up with a butanoyl chloride. Common nomenclature. So on the alpha carbon in common nomenclature, we have a methyl group. And instead of butyric acid, we have butyryl chloride. For carboxylic acid derivatives, common in IUPAC nomenclature are, no pun intended, pretty common and swappable. So you could find either one of these names on a bottle or both. So you're basically just, taking the ic acid out, putting eel chloride, and there you have it. These are going to be, when we go through reactivity, these will be our most reactive of all the carboxylic acid derivatives. Again, why is that? Because the halide ion is a good leaving group. The third derivative, I guess we could do esters are fun. Esters are molecules very typically used to scent things. They smell like fruit salads. So they have either flowery smells or like fruity smells. And a lot of the imitation fruit scents that if one of those people that plugs in one of those like oil air freshener things, you plug it into the wall, that oil, the scent is usually an ester. So we're going to name, so this is where you're going to focus on the group, the alkyl group that is bonded to the carboxyl oxygen. So you're going to name the R group, or in other words, the alkyl group that is attached to the carboxyl oxygen. And that's going to be the first part of the name. And then you're going to follow it with the name of the acid. And that's the carboxylic acid. So I'll just do this to abbreviate it. Replacing the ic acid with the suffix -ate. So that's again, the rule sounds a little confusing, but to see an example might be helpful. So let's go like this. So there, right there, this oxygen is the carboxyl oxygen. The other one is the carbonyl oxygen, okay? So let's put a different R group on the other side. This one you probably used in the lab as a solvent. So you're going to name the alkyl group, right? So the R group that's attached to the carboxyl oxygen first. So this right here is the R group attached to the carboxyl oxygen. This is an ethyl group. And then you notice that the carboxylic acid that this thing came from had 2 carbons. So we're going to say this is ethyl, and that would have been ethanoic acid. But we're going to take away the ic acid and put 8. This is ethyl ethanoate. The common name for this, again, we're going to name the ethyl group first. And that would have been acetic acid, so it's acetate. If you didn't use this as a solvent in the lab, you or maybe someone you know may have used this as nail polish remover. It's nail polish remover that is safe for fake nails because acetone will dissolve acrylic and ethyl acetate will not, but both will dissolve your polish. So this may be a familiar molecule to you. Let's pick something a little different looking for a change. Let's do another example. There's your carboxyl oxygen. There's your carbonyl oxygen, right? So we're going to focus on this oxygen first, or the alkyl group that it's bonded to. We'll get more experience with throwing aromatic groups in there. IUPAC nomenclature will take the name of the R group. In this case, we have an aryl group, not an alkyl group, and it's attached to the carboxyl oxygen. That is not a benzene. It is a benzene ring, but it's when it's a substituent, it's called a phenyl group. So let me circle here. This is the R group that's attached to your carboxyl oxygen. When it is a substituent, it is a phenyl group. When there's a methylene between the oxygen and the phenyl group, it is called a benzyl group. So this would be named phenyl. And then there are 3 carbons that would have been the carboxylic acid, and that would have been propanoic acid. So this will be propanoate. For common nomenclature, we have phenyl, and that would have been propionic acid. So this is going to be propionate. So I was telling you, let me do one more. We'll do one more. Esters are fun. So let's see. We could take that. IUPAC nomenclature. Remember we were saying butyric acid smells disgusting, right? So that would have been butyric acid, right? Or butanoic acid. But you can do chemistry on butanoic acid, or in other words, butyric acid, where you can cook it up with some ethanol. So here's your ethyl group, and that came from the ethanol. So we're going to name the ethyl group first. cook this stuff up with a few drops of sulfuric acid and some ethanol, and you get ethyl butanoate, or you get ethyl butyrate. So it goes from butyric acid to ethyl butyrate. Ethyl butyrate is the imitation flavoring in pineapple lifesavers. A very different aroma than butyric acid. It is almost like magic when you do this reaction. It's pretty awesome. So you could, in the lab, make pineapple oil. It is an oil. So those are esters. And then the last one that we're going to talk about for carboxylic acid derivatives. And when we get to, reactions, I'll bring out the other functional groups. But for right now, for nomenclature purposes, for the sort of celebrity carboxylic acid derivatives, we're going to land with amides. Like the oxidized version of an amine. So we're going to name these by replacing oic acid, ic acid, or ilic acid, depending on the amide you have, with just the word amide. And depending on the ease of speech, some people will have amide, would be sort of just how they say the name of the molecule. Let me give you an example of what I'm talking about. So we've got this, if I were to put a hydroxyl group there, we would have acetic acid or ethanoic acid, right? So instead, I'm going to put an amino group, and the IUPAC nomenclature for that, instead of ethanoic acid, it's just going to be ethanamide or ethanamide. You can pronounce it however you like. This is also the common nomenclature for the carboxylic acid derivative would have been acetic acid. So I'm betting if some of you are bio majors, you've heard of acetamide, and you've taken biochemistry or some kind of like nutrition, sort of some class with metabolism involved. Acetamide is fine, but a lot of people just call it acetamide. What happens? So you're probably wondering, like, hey, we haven't done any with substituents. Let's toss one of those in there. So they're named just like you would name a carboxylic acid, numbers or Greek letters, right? But you're just going to be naming it after the functional group that you have instead of the carboxylic acid. So we could take, like, I guess, a chloro group, and we could have something like this. So IUPAC nomenclature tells us that chloro group is actually on carbon number 3, right? So here we have carbon number 1, carbon number 2, carbon number 3. And the bond from carbon number 3 goes to the chloro group. I'm only pointing this out because it's really easy to forget about carbon number 3. It kind of just looks like the chloro group is hanging off of 2 for whatever reason. That happens to people. So I'm just saying count those out or number them or something so you remind yourself not to lose a carbon. I do it all the time, so it's an easy thing to do. That will be 3-chloro. So what would that have been? It would have been propanoic acid, right? If it was IUPAC nomenclature. So we're going to take away oic acid and add the word amide. So this is all one word here. propanamide. Or propanamide, whatever you want to call it. If we're going to use common nomenclature, we get rid of the numbers and we use the Greek symbols, the little Greek letters. This is your alpha carbon. This is your beta carbon. So we have a beta chloro. That would have been propionic acid. So we're going to call this propionamide or propionamide. If hopefully you're noticing a trend here in that the functional group is the last part of the name on the right-hand side, right? So working right to left, you can build this molecule from the name. You know it's an amide, right? And you might be sitting there going, well, hey, how do you know those are hydrogens? Because you said that it could be an R group. Well, guess what? Let me show you a couple of examples. You would know if you have a substituent bonded to the nitrogen because it would be included in the name. And just like with amines, we're going to tell somebody it's on the nitrogen using an italicized capital N. So, for example, I could have something like this. So instead of hydrogens, I have methyl groups, right, with the line bond structures. Actually, this is all one system, so we'll just do this. We're going to name this using systematic nomenclature. It's totally fine to use common nomenclature, but I'm just going to stick to one right now. You would only be changing the common name of the carboxylic acid if it has 6 carbons or less. But you want to tell somebody that you have 2 methyl groups and they're both bonded to the nitrogen. So you have 2, not just 1. I've seen people do this where you have 2 substituents hanging off the same carbon and you only write the number down once. You have to write it twice and you have to separate those numbers with a comma, even if they're the same number. So N comma N dash dimethyl and what is that? That has, let's count them up. 1, 2, 3, 4, 5 carbons. So this would be, instead of pentanoic acid, it's pantanamide or pantanamide. You could also say NN dimethyl valeramide if you want to use common nomenclature. What about this? So we could have like we could have 1 R group on the nitrogen instead of 2. We don't very often use rings as substituents, but we can right now. You want to tell somebody that you have a cyclohexyl group on the nitrogen, so it's N-cyclohexyl. And in the parent compound, we have 1, 2, 3, 4 carbons. So that would have been butanoic acid or butyric acid. So we have cyclohexyl butanamide. Or if you wanted to name it after common nomenclature, we would be dropping ic acid instead of oic acid, right? And it would be N-cyclohexyl butyramide. So those are the same. And again, if it's common nomenclature or IUPAC nomenclature, you have substituents elsewhere, you can add those in as well. You know, if you have a group on the nitrogen, you're going to name that first, just like with an ester. And then if there's a substituent on the molecule, it will come after the alkyl group on the nitrogen. Or if you have an ester, it will come after the alkyl group on the oxygen, the carboxyl oxygen. So you just put a hyphen after that alkyl group. You'd give the number or the letter, depending on what system you're using. You would state the substituent, and then you would carry on from there. It's literally just, if you imagine drawing the structure from the name, you're going to be working from right to left. If you're going to be looking at a structure and then naming it, you're going to write it down from left to right. Either way, you should be able to either draw a structure or a name from a structure just by looking at it. So that's going to do it for structure and nomenclature. In the next video, we will discuss structure and then physical properties. That'll include electron geometry, resonance structures, boiling points, any kind of physical properties, reactivity, any of that kind of stuff. And then I'm going to make a third video just for reactions.